Less so, I think, to convex bodies that are not polytopes. So in this lecture, I'd like to ask the following question. Let's take the simplest example of a variety. Let's take an algebraic curve in space, in three-dimensional space, and let's calculate the convex hull. Okay, what can we say about the convex hull of a curve in three-dimensional space? So here's a picture, for example, of a knot. That's a curve in 3 space, and we'd like to calculate the convex hull. And everything I say in this second lecture is joint work with Christian Ranestad in Oslo. Here's one example. Let's take a trigonometric curve parametrized by cosine theta, sine 2 theta, cosine 3 theta. Now, those are, of course, polynomials, right? Secretly, trigonometric functions are polynomials, so we can rewrite this as the intersection of a quadratic surface and a cubic surface in three-dimensional space. So that's a space curve of degree 6. How do you find these polynomials? Well, my daughter a little while ago in 11th grade in high school took 7 weeks of trigonometry. Now, I didn't know that there were 7 weeks worth of trigonometry, but one of the things you learn in trigonometry is that cosine 3 theta is a polynomial in cosine theta, right? So that's called a Chebyshev polynomial, and there it is. Okay? Let's look at this curve and calculate its convex hull. So this picture is the convex hull of this curve. The curve is in blue. It snakes up like this, comes down, comes up on the back, goes down again. So in blue, we have this degree 6 curve. And I've drawn, or Frank Sotila has drawn, the boundary features of this object. First of all, this body has 2 flat triangular faces. Right? So there's a top triangle up here, and then by symmetry, it rests on a triangle down there. So there are 2 flat two-dimensional faces. Those triangles span tritangent planes. So there's a plane that touches the curve at 3 points, making a triangular face. In yellow and in blue and in green, you have the nonlinear features in the boundary, and these are curves of edges. So these are ruled surfaces. So here in yellow, you have a family of edges that forms a yellow ruled surface, and over there you have in green another surface. And I would like to calculate this exact boundary description. So I'd like to write a program where this is the input and an exact description of this is the output. Question? Well, it's a union of lines, right? So here I simply mean, so this line is actually in the surface, and I'm just taking, and I'm moving the lines. They move in a one-dimensional family. So let's just say a ruled surface is it's a curve of lines. Oh gosh, I think it's something slightly different. Actually, I forgot some of the classical terminology. But I think in this case, since a convex body, we have a notion of edge, right? So there's an exposed edge. So these are exposed edges, meaning a linear functional actually attains its minimum. There's an edge out here that's not an exposed edge, right? This edge of the triangle is not an exposed edge of the body. So we have to be a little bit careful when we talk about faces, but this is it, okay? Now the next slide shows what I will not do, but what Tim would do. I think most people in this audience would do the following thing. They would say, this body is a spectrahedral shadow. That is to say, I can write this as the projection of a spectrahedron. I have an LMI representation. So I will not write this body as a projection of this 6-dimensional spectrahedron. So here I have a Hermitian 4x4 matrix. Another miracle of math is that Hermitian matrices have real eigenvalues, that it can be positive definite. So if I look at in x, y, z, u, v, w space, a 6-dimensional space, I have a 6-dimensional spectrahedron given by the positive definite condition, I is the square root of -1. Then I claim that by eliminating u, v, and w, I get exactly this body. Okay? Well, that would have been probably Tim's answer, possibly Tim's answer to how to represent and compute this object, to write it as a projection of a 6-dimensional spectrahedron I've given you that representation, but I do not want to talk about that. And the reason I don't want to talk about it is because this representation does not reveal the nature of the green surface and the yellow surface. It doesn't give me the degree or the equation of these objects. So I like to actually give you these equations. So this is a workshop and tutorial on polynomial optimization. So I'm the guy who's supposed to give you polynomials. Okay? Now the yellow polynomial, that's our little Chebyshev cubic, right? So that's the Chebyshev cubic surface we've seen already, but the green one is more interesting. So the green surface has degree 16, and this is its irreducible defining polynomial. This is the unique up to sign irreducible polynomial in x, y, and z that cuts out the green surface. So I'm interested in this. So these kind of small polynomials, when compared with that, small polynomials, I find them very beautiful. So I like to write a computer program whose input is cosine theta, sine 2 theta, cosine 3 theta, whose output is this description. Okay, any questions? I'd like to tell you a little bit about these surfaces.
Could you obtain this equation by elimination from the rank?
Yes.
Rank drop?
Yes. So I like to. So I have a program in Macaulay 2 that takes this polynomial and then carries out a certain elimination, and it makes that polynomial.
Okay, so it's not related to the previous matrix.
Oh, I see. Can I get, yes. So in principle, yes. So can I get it from this representation? Yes, absolutely. In principle, I can also take this representation. I can then look at the critical locus under this projection and also compute it. This I have not succeeded with. But in principle, yes. Yeah, now understood the question. Okay. So let me tell you a little bit about these boundary surfaces. So I'm going to now, this is now the part where I'm actually going to talk about algebraic geometry. So fasten your seatbelt. So C is a compact algebraic curve in R3. And I'm going to make my problem easier. Whenever we deal with polynomials in an applied situation, what an algebraic geometer would do, we might make the problem easier in 3 steps. Step 1, we disregard all inequalities. Not because they're not important, they're very important, but we just want to answer an easier question first. So let's just forget about inequalities for the moment. The second thing we're going to do, we're going to replace the real numbers by the complex numbers. Now that makes the problem really easier, right? Now the quadratic formula, right, always has 2 roots, right? So we're going to replace real numbers by complex numbers. That makes the problem a lot easier. And the final simplification step is we're going to replace affine space by projective space. That makes the problem really easy because now any 2 lines in the plane will meet. Any 2 circles in the plane meet in 4 points. Folks in the last row, any 2 circles in the plane meet in 4 points. Okay? So now the problem is easy enough so we can actually say something about it. So let me write by C bar the corresponding curve in complex projective 3 space. Now such a curve is a Riemann surface, right? The complex plane is called the complex plane because it has twice the dimension of the real numbers. So a curve over the complex numbers is a surface over the real numbers, and it's called a Riemann surface. The 2 basic invariants of such a curve or Riemann surface, first of all, there's the degree, d. That's the number of intersection points with a plane in 3 space. So if I have a curve in 3 space, the degree is the number of intersection points with the general plane. And since I made the problem easy, it doesn't matter which plane I've taken. Right? That's the degree. The second number is the genus, G. Well, it's a Riemann surface, orientable, right? So it's a donut with a bunch of holes, and the number of holes is the genus. That's G. Okay? I'm going to say my curve is smooth if and only if the complex projective curve is smooth. So I might show you a real picture that shows no singularities, but maybe in the non-beeping part outside in the imaginary world, there might be some singularities. I'm not going to allow that.
I have a naive question.
Yes?
Two things. How do you generate this C bar?
I don't do anything. I see. I have my equations.
C you have.
Yes, just a second. So I'm given the C. So C is the zero set of x squared minus y squared minus xz, and z minus 4x cubed plus 3x. So to pass to the complex numbers, I just take the same equations. I just allow x, y, and z to be complex. To pass to projective space, I add in a homogenizing variable, w, for example, and I homogenize the last equation. So the last equation now is z times w squared minus 4x cubed plus 3xw squared. So w equals 0 is the plane at infinity. So I'm just replacing non-homogeneous polynomials by homogeneous polynomials in one more variable. I don't do anything else. Okay, that's C bar. The convex hull of a real algebraic curve, such as the cable, is a compact, convex, semi-algebraic subset in 3-space. And by Tarski's theorem on quantified elimination, the boundary is a pure 2-dimensional semi-algebraic subset of 3-space. Okay? So I have a 2-dimensional semi-algebraic, just means given by equations, Boolean combination of equations and inequalities. Now I'd like to make this a little easier by replacing the boundary by the algebraic boundary. Let me define the algebraic boundary. K is the field over which the curve is defined. So this is a subfield of the real number. So typically, very often for me, K will be the field of rational numbers. Now I like the rational numbers because I can send you scalars over email. Okay? I don't like the real numbers because I'm dead before I meet them. I cannot send you a real number over email. Okay? But I can send you a rational number over email. So let's say K is the rational number. So then the algebraic boundary is the K-Zariski closure of the classical boundary. And this I'm going to denote by D sub A. So this is a complex surface. It's usually reducible, and it has a unique up to scaling, defining polynomial. Let me explain this in an example. So suppose I have the following task. Suppose I give you 4 points in the plane. And I like to compute the algebraic boundary of the convex hull. So I give you 4 points in the plane, but I give them to you as the intersection of 2 conics. Okay? 2 general ellipses. And I want to calculate the boundary in this sense. Okay? Now what's the algebraic boundary? Well, first of all, what's the classical boundary? The classical boundary is you draw these edges, and we call this a quadrangle. Okay? That's the classical boundary. Now we want to disregard inequalities. So the algebraic boundary over the real numbers is the union of this line, this line, this line, and this line. This is the algebraic boundary over the real numbers. It's a quartic polynomial in the plane that factors. But real numbers, hey, you can't email them. So let's take the algebraic boundary over the rational numbers. The algebraic boundary over the rational numbers is an irreducible curve of degree 6, namely this curve. Right? Over the algebraic numbers, over the rational numbers, I cannot distinguish these 6 lines. The Galois group acts transitively. So the algebraic boundary of the quadrangle over the rational numbers is this polynomial of degree 6. Okay? That's how it goes. Here's the theorem. Suppose C is a gentle, smooth, compact curve of degree D in genus 3 in 3-dimensional space. I've defined every adjective except for the adjective general. I won't define it. I'll be happy to talk to you about this over coffee. Okay? Then the algebraic boundary of the convex hull is a surface. It's given by a polynomial in x, y, and z, say with rational coefficients. And it has two parts, a red part, which we call the edge surface, and the blue part, which we call the tritangent planes. And the edge surface is a surface of this degree, 2 times d minus 3 times d plus g minus 1. And then there are those triangular faces, and we count them by counting tritangent planes, complex tritangent planes, and the expected number is this blue number. So a tritangent plane is exactly what you think it is. It's a plane that's tangent to our complex curve at 3 points. Okay? Now, if you think over the real numbers, 3 things can happen. You could have a tritangent plane that's actually complex, right? You need complex numbers to write the plane down. Or you could have a real plane. But then there are 2 subcases, right? That real plane could touch the curve at 3 real points. Or it could touch it at 1 real point and 2 imaginary points. All of these things are counted here. Okay? Now, the hard work was done by others. So there's a book by Joe Harris and collaborators on algebraic curves. In the last section, in the last chapter, you find something called the Jonquier's formula, and that implies the blue number. Let's talk about the nonlinear part, earlier seen in green and yellow. Suppose I take 2 points on the curve. Here's my curve. Well, it's a smooth curve, right? So every point has a tangent line. So 2 points have 2 tangent lines. So for 2 general points, these tangent lines won't meet, right? They won't lie in a plane. But if I have 2 special points, they might meet. Okay? So I'm going to say that a secant line between 2 points, P1 and P2 on this curve, is a stationary bisecant if the tangent lines actually meet, if they lie in a common plane. The edge surface is the union of all stationary bisecant lines. So to answer Bernard's question, I carry out this elimination. I write this in terms of polynomials, and I carry out the elimination. Again, the hard part was done by others. So Arondo and co-authors in 2001 found the red formula for the degree. A picture says more than 1,000 words, so let's see an example. Let's look at d equals 4 and g equals 0. So g equals 0 means it's a Riemann surface without holes. So it's the Riemann sphere, right? Rational curve. And we're going to look at a quartic curve in 3 space that's rational. So in this case, the blue number is 0. There are no tritangent planes. And then the stationary bisecants, the edge surface, will be a surface of degree 6. Here it is. So for sake of concreteness, let's do a trigonometric parametrization, cosine theta, sine theta plus cosine 2 theta, and sine 2 theta. So that's d equals 4 and g equals 0. So in the picture, the curve is in blue. You can see it goes up, comes down on the back. Can you see that, folks, in the last row? Yeah, the blue curve. Lady with the white shirt, can you see the blue curve? Okay, so that's the curve. We want to calculate the convex hull of this dark blue curve, and we're going to solve the easier problem of calculating the algebraic boundary, and that's this purple surface. This purple surface is a surface of degree 6. It's an irreducible surface of degree 6. You can see it's single along the curve, right? It self-intersects on the curve. So the actual boundary is the stuff here, but then, if you want to pass from the algebraic boundary to the actual boundary, then you have to crop off this other stuff, right? So, but any exact representation of this algebraic, of this convex hull, uses this degree 6 polynomial. You can try this at home. So in the US, we have potato chips called Pringle. Take a Pringle, take the convex hull. So if you take a Pringle and wrap it in Saran wrap carefully, you get that surface. Okay. Any questions? Any of the experts, the non-experts, have any questions? Is it clear what we're doing? So this is the exact representation of the convex hull of the blue curve. I think I'm doing well in time. Let me talk a little bit about another case of quartic curve. So one way you can make a quartic curve is to intersect two quadratic surfaces. So if you have two general quadratic surfaces, Q1 and Q2, you intersect them, that also makes a surface of degree 4. But that's now genus 1. That will be an elliptic curve, the ones that your cryptography friends like. Okay? So that's G equals 1 and D equals 4. So if you take a soccer ball, British football, you intersect it with the boundary of an American football, then the intersection will be such a curve. And we're calculating the convex hull of that curve. Now, the red number is 8. The edge surface has degree 8. And this is an interesting example because even for general such curve, the edge surface will always be reducible. It will be the union of 4 quadratic cones. And here's a little proof how you calculate that by resulting calculation. So the moral is that even if you have a curve that's general and smooth and irreducible, the edge surface might have multiple components. This is what happens for the genus 1 quartic curve. Couple more words about trigonometric curves. They're always fun, you know. They are nice to make examples. And of course, you know, trigonometric polynomials also played a big role in Emmanuel's third talk. So by a trigonometric polynomial, I simply mean a linear combination, alpha j cosine j theta, beta j sine j theta. Anything that's parametrized by 3 such things is a trigonometric curve of degree d. These things will be smooth Riemann spheres, g equals 0. And as your trick for writing this as polynomials, right? So you can replace cosine theta by this rational function in one variable t, sine theta by that rational function. The sum of their squares is 1. And then, you know, if you take this rotation by angle theta and do it j times, that's the same as rotating by angle j theta. So this is how you take the trigonometric representation and turn it into a parameterization by rational functions. This was on Tim's slide. Also the same picture. This is an example for d equals 6, g equals 0. So this was the algebraic rational curve of degree 6. In this case, the numbers in the theorem was 8 for the tritangent planes and 30 for the edge surface. For this very special trigonometric curve, we get this colorful cheesecake picture that you saw in Tim's talk already. So the curve again here is in blue. It comes up, it goes down in the back. There are some triangles. And then I think the green surface, again, I think has degree 14 or 16. Now, when we started this, there wasn't much to be found, actually, in the literature. So if you look on the net, on the internet, well, there's some information about the convex hull of curves. So we came about one thread of the literature. So Mike Friedman, the Fields Medal winning topologist, wrote a paper in 1980. And in that paper, he asked the following question, whether every knotted curve in R3 must have a tritangent plane. Okay, so imagine you have this curve made out of wire, and you drop it on the floor. Okay? Now, there are 2 ways it could come to rest. Either it's in a stable position, then the floor is a tritangent plane. Or it could come to rest as like a rocking chair. Right? That's a stationary bisecant. You can imagine, right? You have the curve, you drop it on the floor, And it seemed to be the case that every knotted curve always has one way of dropping on the floor so that it rests stably as a tritangent plane. Well, that was disproved in 91 by Morton, and this is a counterexample. I just give this, because the Macaulay 2 program I'm describing in this lecture will do this automatically. Right? So you type this in, you calculate the edge surface and the tritangent planes. You look at whether there are any real tritangent planes that touch the curve in 3 real points, and the answer is yes. Okay. Singularities. So the theorem I stated was only for smooth curves. We have a little bit of information for curves with singularities. So this theorem says that the edge surface will drop in degree by 2 for every ordinary singularity. So a singularity could be a cusp or a node, and whenever there is such a cusp or node, it drops by 2. So again, I'm going to illustrate this by a picture. So I'm going to look at the case of rational quartic curves that have either one node or one cusp. In this case, the edge surface has degree 4. It's the union of 2 quadric cones whose intersection equals the curve, and there's a small difference between the two, which I will visualize in these diagrams. The curve is white. So this is a rational quartic with one nodal singularity. You can see here in white there's the node. You take the convex hull, so the algebraic boundary has degree 4. It splits into 2 singular quadrics, the red quadric and the blue quadric. Right? So they look like cylinders. That means their cone point is far away. Remember, we put the plane infinity in to make it easier. So the cone point is far out on the red quadric and on the blue quadric. So this is a rational quartic with a node. The rational quartic with the cusp looks like this. Again, there are 2 singular quadrics, but now one of them has its cone point at the cusp. So you can see the curve is in white. It comes up, goes down, and then this is the algebraic boundary of the convex hull. Okay, questions? Okay, Pablo.
So, for the tritangent planes, I mean, somehow the Morton example that you gave, that shows that none of the planes, they have to be real.
That is correct. No, there is one real, but it doesn't touch the curve.
Oh, I see.
So this one actually has a real tritangent plane, but it touches... I'm sorry, I take this back. No. It touches at one real point and 2 imaginary points.
Oh, I see. But what about the converse? I mean, how many can you make? I mean, you have this number. Can you make all of them real?
That's a very good question. I don't think so. So I don't know. In the plane, the answer is yes. So for plane curves, by tangents, you can make them all real. I don't know the answer to this question. My guess would be the answer is no. So the question was, I have this complicated blue expression worth of tritangent planes. Can I arrange for a curve that has all of them real? I don't know the answer. Very good. It's a constants question. So experts in real algebraic geometry can maybe look at this. Okay, pretend for a moment this were a pure math audience. What's the question you're supposed to ask next? Diane, what's the question you're supposed to ask? So I talked about taking the convex hull of an algebraic curve in 3-dimensional space. A 1-dimensional variety in a 3-dimensional space. What about the general case? Exactly. When can you do this? Is this restricted to, well, okay, there we go. So yeah, let me talk for a couple minutes. Let me give you the general theorem. So X is a compact, real algebraic variety in n-dimensional space of any dimension. Again, I'm going to make the problem much, 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 much easier by passing to X bar. That's the complex projective variety. I'm going to assume for the moment it's smooth. I'm going to pop open 2 windows, one for the first projective space that has points and hyperplanes. That's CPN.
Could you just turn off your mic?
Mic went off.
Your microphone.
Microphone.
Oh. Maybe it's out of battery. Where it's no longer green.
Somebody coming.
What happened?
The battery. Mic was off.
What comes light? No light. Okay, well then I have to come into the back. Okay, so I go right in the middle.
Fine.
So we have two windows, one for CPN and the other one for the dual CPN. Check. So the points in the first correspond to hyperplanes in the second and vice versa. So let's look at the following object. X upper K is the set of all hyperplanes that are tangent at K affinely independent points. So I start with my cable, my first variety. I look at all hyperplanes that touch at K points that are affinely independent, and I close it up. Okay? Now that's a variety, X upper K, in the dual space. So in particular, X upper 1 is the classical dual variety. It's a set of all hyperplanes tangent at one point.
The microphone's off again.
Okay, well, we're going to do without microphone. So I have an inclusion, x1 contain xn and so on in x2 and x1, right? So the I'm getting some overtime. Huh? Injury.
I have to speak loud and
Yeah.
pick you up.
Okay, I'm going to stand right to this thing. So I have this inclusion, right? x2 is contained in x1, right? Because those planes that are tangent at 2 points lie in the closure of those that are tangent at 1 point. Okay. So now I'm going to double dualize. I'm going to look at x upper K upper 1, right? So that takes us from the first window to the second window to the first window, right? So I dualize back. So x upper K lies in the original space, and that's the object I'm going to be interested in, x upper K dual. Now for small k, this is the classical secant variety, but I'm not going to be interested in that. I'm going to be interested in large values of k. K is at least this number. I'm going to be interested in the case when this x upper K star is a hypersurface. Dimension 1 given by a single polynomial. Then we have the following general theorem. So we're interested in the convex body, so the convex hull of X. That's a compact convex body in R to the n. The algebraic boundary can be computed by projective biduality by the following formula. This algebraic hypersurface is contained in this algebraic hypersurface. It's the union over all k of x upper K dual. I would like to have an equality here. But I can't get that. That's the best I can do with purely algebraic methods. What am I saying? This is given as a product of polynomials in n variables. Right? So I take a product of polynomials in n variables. This is given by a subset of those polynomials. So I have a hypersurface containing another hypersurface, and it's given. Convex hull, right? So that requires a separate calculation using real numbers and inequalities and STP and so on. So this is the best result I can get by a purely elimination type calculation. So that's the general theorem. Let's go over some examples and then wrap up. So plane curves. So suppose I have a curve in the plane. Then the theorem says it's x upper 1 dual, that's x itself by biduality, union x upper 2 star. So how do you calculate the convex hull of a curve in the plane? Well, if you have a curve in the plane, there are two features. One feature is the curve itself, and the other feature is the bitangent lines. So x, the curve itself, and then up there we have x2 dual. That's the bitangent lines. And then the classical formulas that count the number of bitangent lines, and those, Pablo, can be all real. Space curves we've seen. So in the space curve case, we have x upper 2 dual. That's the edge surface. We have x upper 3 dual. That is the triangles, the tritangent planes. You can look at surfaces in 3 space. There you have all 3 features. So for a surface in 3 space, you have in the convex hull, you might have a little bit of the surface itself. You might have a little bit of tritangent planes, triangle, flat faces, but you also have an edge surface. Okay? And then here are some numbers that give you the expected degrees. And you can see the number of tritangent planes. That's a result from the 70s by these authors. That's some complicated polynomial of degree 9, right? And you could ask the question, can you make them all real? We don't know. In practice, when you look at a surface and you want to actually describe the convex hull, these will be highly, highly, highly singular, and the degree will be much smaller. So beautiful galleries on the internet. So in Germany, they had the year of mathematics. So they're beautiful, galleries on the internet of algebraic, singular algebraic surfaces, such as this citrus surface, and there the algebraic degree of the boundary will be much smaller. The last slide. Maybe I lost some of the non-experts along the way, and possibly some experts as well. And here is the last slide that's understandable to absolutely everybody. Take a coin. Okay, maybe a €1 coin, let's say. Take 4 of them. Take 4 identical coins and make them touch pairwise. Okay, so form a tetrahedron out of 4 identical coins. Take the convex hull. Okay. Well, that's an example, right? The boundary of those are 4 circles, right? You have 4 pairwise touching circles in 3 space. That's a reducible singular curve of degree 8. Let's calculate the convex hull. Now, in the first talk, we glued in the quartic Steiner surface to get the dual Somoza. But now we're not going to glue anything in. We're just going to take it as is. We just take the convex hull of 4 identical coins. You can try that now. Okay? Take 4 coins, make them touch, take the convex hull. Now, this is already a nice example that shows the features we discussed. So in every hole, there will be a tritangent plane. There will be a small triangular face appearing. But that's not enough. There's still holes. And what we'll see are 6 quadratic surfaces, ruled surfaces. So here, these 2, for every touching point of 2 coins, there will be a little bit of a quadratic surface. So already this example illustrates the features we discussed. This, of course, is what polytope people call a Schlegel diagram, right? So Schlegel diagram means you take the convex body, imagine it's made from glass, and you put one of the flat faces in front of your eyes, and you see this, right? So 1 coin is sort of at the outside, and then you have 3 small coins. So this shows the convex hull of 4 pairwise touching circles, and it shows the features we discussed in this lecture. And I leave it as an exercise or exploration for the non-experts to take more coins and put them in various positions and see what you get in the convex hull. The experts are invited to tell me how many terms are there in the boundary, algebraic boundary, in the cone of convex binary sextics. Thanks for your attention. Let's take a coffee break.
The complex are R2N, let's say.
That would take, consider the complex structure somehow?
Yeah, for the convex hull of a surface, and in the complex R2N Cn.
I mean, you could certainly regard Cn as R2n, but you have something in addition in mind that would.
Not just that, because it's always looking at this geometry, algebraic geometry tools, with complex, consider complex number, and then back to the reals at the end.
I
right?
see. Yeah. Well, I guess you could do that. Then, in that case, it would be a special case, right? It would be just an even ambient space.
Nobody looks at that, like convexity in the complex plane, for example.
I see. We haven't looked at it. And I know in complex analysis, you know this, there's a notion of convexity and pseudo-convexity. I have not looked at that, whether that would interface with this.
It's different.
It's different. I think it's quite different.
Can the optimal solution of a semi-definite program be represented using radicals?
Not in general.
Right.
Not in general. So there is a study. I was involved in a paper a little while ago called the algebraic degree of a semi-definite program. So there we asked the question, what is the intrinsic algebraic complexity of solving a semi-definite program? So by that I mean, what is the degree of the optimal solution? So the optimal solution for a linear program, that complexity is 1. Right? So for a linear program, no matter what you do, if it's the data are rational, it will be rational coordinates, and you have a concept of rounding that lets you recover that true real rational number. So for a semi-definite program, these will be algebraic numbers, and of course the way we solve them, we only get a floating point representation of that algebraic number. But the true number, of course, is an algebraic number of a certain degree, and there's a formula for that degree, but it can be very high. It depends on 3 things. It depends on the size of the matrix, so n by n matrix, depends on the dimension of the slicing space, and it depends on the rank of the optimal solution. So there's a range of possible ranks. So there's a table, depending on those 3 quantities, what the algebraic degree is. But it can be big.
Last question. If I mix theta with cosine theta, what is the complexity for a symbolic manipulator?
So the question was, if I take both theta and cosine theta.
Something very simple, low degree.
Yes. So this, I don't know. I think this has been studied by people in France, like Van der Hoeven, maybe. So what happens if you have theta? Then of course you're no longer algebraic, and you're then you're really in a transcendental setting. I believe that people have looked at elimination problems like that. I don't know. The top of my
You
head.
might be in trouble immediately that the result will not be in that form anymore, right? Like if you have an exponential and polynomial, then the things are not. It's called
But isn't that decision? At least
in this all minimality business, people.
But I think there's a decision procedure.
Yeah.
So we can answer yes, no questions, but to write down, my elimination will be more complicated. I think people are ready for a break.
So we'll have the afternoon break, tea, and we'll reconvene at 4.